So we'll be discussing stream processing in the network security domain. And just to introduce ourselves, I'm the lead of the detection automation team. And our team's job is to help our security analysts avoid the noise and zero in on the actionable intelligence for our customers.
Hi, and I'm Jonathan Walsh. I am a member of the Threat Operations and Analysis team, and we utilize the technologies that Ray's team provides in order to tune and focus our threat analysts towards what we're looking for, what's the actual attacks that we want to detect. So you heard we mentioned SOC as a service. Just to understand what a SOC is, it's a security operations center. If any of you are familiar with what a network operations center is, it's similar in a way. We're looking for observables on client networks or on a network level that indicates an attack or some sort of compromise is going on. So that might be a firewall log, that might be an antivirus log, that might be an IDS log, or Active Directory authentication. I could literally go on for about an hour. What we do is that we provide this service to our customers. Essentially, we have our in-house security experts. We deploy sensors on to their network environments and also hook into their cloud environments in order to get these observables, these events, down into our data stream. So our team of security experts look through these events, look for attacks, and we want to make sure that we're letting our clients know about something that is an imminent danger that they need to deal with. So what that means is that we need to focus in on actionable data. There's a balance between informative and being noisy. We could certainly alert on a lot more and miss nothing, but if the client is getting overwhelmed with the number of alerts that we're sending them, that's no good anyways. There's obviously everyone's heard of Boy Who Cried Wolf. We need to make sure that we're only crying wolf when there's something that they need to deal with immediately. And this is a quote that I like regarding that. So to discuss a little bit about how we do that and how threats are modeled in production, Lockheed Martin came out with this, what they call the cyber kill chain or attack chain to describe how a network attack operates. So this in particular is for a network intrusion. So what might be doing is typically they follow through these steps when attacking a computer network. So typically you have your reconnaissance step looking for, trying to gather data on your end target. This might be as simple as a port scan on the internet, or it might be as sophisticated as someone walking up to you in a conference and talking to you, getting more data out of it. There are a wide range of different possibilities for that. Typically, once you have information about that, you're doing the weaponization of your attack. So whether that's creating an exploit to attack what you've discovered within your reconnaissance standpoint, crafting phishing, spear phishing, those sort of attacks, delivering the bundle to the client, the end target, exploiting them, installing the malware, and then once you're in the malware, what you want to do is establish communication back to the what they call a command and control server. So a server on the internet that the attacker controls. This could be another compromised system. It could be a server in Russia or China or places that don't work well with US subpoenas. And then once you have your command structure in place, you're doing your actual attack objectives. So to get, whether that's harvesting email information or damaging computer networks. To give an actual real example, some of you may have heard of the WannaCry ransomware. Essentially, one of the methods that might be used to implement and have this attack is via social networking. So what they what an attacker might do is look for the targets that they're trying to attack, the target organization, look at their employees, go on LinkedIn, take a look, see. Now, typically, most organizations follow a very common email scheme, so harvesting email addresses is going to be dead simple if you know it, or you can put 2 and 2 together. So the weaponization point is that building that ransomware binary. So you can go on the black market, buy it, build it yourself. It's all available. And they do a spear phishing attack in order to deliver this. So send an email to Linda in accounting, not to pick on Linda, but you can send an email, and then as soon as it's exploited, they establish that command and control back, and that's typically within ransomware to exchange encryption keys, to provide information so that the ransomer knows the target, knows the value of it, and has the key for decryption if they pay the ransom. Now, the attack on objectives in this case with WannaCry is that it was a little unique in the ransomware field in that it was working as a worm as well. It was spreading laterally over PowerShell and SMB, Samba or TCP/445, Windows file sharing essentially. And it was spreading out initially, so it wasn't just encrypting what the user had access to, it was encrypting the entire client networks. So what was happening is that everyone was, you could clean like half your network and it would just get reinfected as soon as it gets brought back on the network. So when we're looking at attack chains and looking at indicators, each of these steps can be incredibly noisy. So I mentioned port scans or vulnerability scans during the reconnaissance step. That's happening constantly. It's every second you're getting scanned. That might be an exaggeration, but still, you're getting scanned constantly on the internet. If we're alerting our clients every time they get a port scan, they're going to have no use for us. So we want to make sure that we can correlate these events, correlate steps in this attack chain in order to provide meaningful information to our clients.
Thank you, Jonathan. So Jonathan talked about what it is that we want to detect, and I'm going to go through how we do it. And to start with, I want to talk about our data sources at a high level. So at the center of it, we have an on-premise sensor. It's a hardware device that we deploy in the customer's network. It has 2 main functions. First of all, it provides visibility into what happens on the customer's network. It monitors network traffic. Anytime there is an HTTP transaction that crosses the sensor, anytime there is a DNS transaction, DNS lookup and reply, or even any sort of TCP or UDP flow, the sensor will generate an event. And that event is then sent into our cloud, into our cloud for further processing. In addition to that, our customers have a large number of infrastructure devices. So they may have routers, they may have switches, they may have proxies, they may have Active Directory servers. Our customers can configure all of those to send their logs to our on-premise sensor. Every log line is converted to an event, and the sensor, once again, then sends up the log lines into our cloud for further processing. Finally, we have our cloud data sources. So these are things like AWS, Azure, Office 365, SaaS services like Salesforce. Once again, our customers can set them up to be pulled by us, and we have pullers that reach out to these services and retrieve logs indicating what is happening with these services. These, once again, go into our cloud for more processing. They do not cross the sensor, the on-premise sensor. They go directly into our cloud. What we ultimately want to be able to do, as Jonathan said, is be able to correlate multiple events across potentially different data sources and provide actionable intelligence. So first and foremost, we want to provide intelligence to our security analysts who work for us in our SOC. And our security analysts need to then go and escalate issues that are of interest to our customers. We process over 30 billion events every day across our entire customer base. When we submitted the stock back in November, we were at 9 billion. We've gone up substantially since then, and this is continuously growing. And so it is not feasible for our security analysts to go and try to pick out these patterns themselves in these various streams. And essentially, that is what we're dealing with. We have a large number of unbounded streams that we have to somehow process. We started looking into this domain area about a little over 2 years ago, and we started looking to see how it is that we can more or less declaratively specify the patterns that we want to find in these event streams and automatically find them. We very quickly came across the complex event processing field. And once we did that, we started looking into platforms to build our complex event processing offering on top of. And at that point, we very quickly found Flink. So why Flink? Flink is built for streaming from the ground up. And like I said before, we're dealing with a large number of unbounded streams. Flink has built-in support for out-of-order events. And that's something that comes up a lot in our areas. Even within each individual data source, events often can appear to come in out of order, not necessarily in the order of the timestamp. But especially once you start correlating across different data sources, you're guaranteed to have that. So we want something to deal with that for us, and Flink fit the bill very nicely. Finally, horizontal scalability. So with Flink, we can deploy a cluster. We don't need to worry about the horizontal scalability. We don't need to worry about the communication between the task managers, between the nodes. We write the business logic. Flink takes care of everything else for us, more or less. When we found Flink, we also found Flink CP. Our experience with Flink CP dates back to 2017, and I know that a lot of work has gone into Flink CP since then. At the time, and I can't really speak to where Flink CP is today, at the time, about 2 years ago, we couldn't really make it work for us for a number of reasons. So number one was that expressivity. It wasn't really where we needed it to be to express the patterns that our security analysts were looking for. Things like counts were not part of Flink CP since then. And I've looked at documentation on the website just the past week for Flink CP. I know that it's come a very long way. But my exposure to the newer versions is basically reading documentation, so I can't really speak to it directly. The other issue, and again, this was 2 years ago, was the scale. And I believe, again, a lot of work has gone into it since then. At the time, we were dealing with about 2 billion events a day. And even the rules, the patterns that we could express with Flink CP, we couldn't really get it to work at scale. So unfortunately, we had to give up on Flink CP. And we moved on to Esper. So Esper is a mature and expressive streaming complex event processing engine. It's available both for JVM and .NET. It is open source software with some pay-for offerings if you need some extra functionality that doesn't come as part of the open source. In Esper, you express queries in EPL, which is a SQL-like event processing language. The Esper documentation is very, very, very comprehensive, very, 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 very long. It's about 1,000 pages in total, so I cannot do justice to what EPL is capable of in this presentation. But I just want to give a very quick primer to give a sense of how we express some things in EPL at a very high level while glossing over some details. So previously, Jonathan was talking about being able to detect the spread of ransomware. And he was saying that ransomware spreads can spread horizontally. And so we want to be able to detect PS exec services. And a PS exec service, when it gets created, lets you execute arbitrary PowerShell code, for instance, on a Windows device. We want to be able to detect PS exec services being created on at least 10 distinct devices in a time frame of 5 minutes. So we have something that looks very much like SQL, but is obviously not SQL. So we started with a select. You select something from a stream. And PS exec event here is the name of the stream and also a typed event with properties. And then you specify a time window. So in our case, a sliding time window. We say we want to look 5 minutes back at any given moment. The hash marks are stream compositions. So these are all stream operators. So first we say, OK, We have our stream of pxexec events. We want to retain 5 minutes worth of them at any given time. And then we want to look at unique target IPs. And target IP here, is just a property in the psexec event. So we want to have a window looking 5 minutes back, retaining events with unique target IPs. And we want to accumulate events up to the point where we have 10 events in this window. When we have 10 events in this window, we emit a match. Okay? So here we're basically looking for fairly simple sliding windowing logic with some distinctness constraints applied to them. Now, let's say we want to do something else. We actually care about the order of events for this one. So we want to be able to express a pattern for endpoint virus detection, followed by a network IDS intrusion detection system detecting sort of an exploit. And so again, we have EPL come into this. So we're starting with the select. The pattern keyword introduces a pattern where the order of the events matters. And we're looking for an antivirus event, which is, again, a type of event, followed by the arrow is a follow by operator, an IDS exploit event, and we say we're timer within 15 minutes, which imposes a timeout on the length of this entire match. So if we don't see an antivirus event followed by an IDS exploit event within 15 minutes, the match times out, and it starts looking again. So we've talked about windows, time windows, sliding time windows. We've talked about EPL that looks for events in a specific order. Now, let's say we actually want to combine the two concepts. So this is a wall of text. I'm not going to go through all this in great detail, but just to quickly gloss over things. So here we're looking for a successful brute force attack. So for example, we want to look for somebody trying to log in to a specific user account, failing repeatedly, and then being able to log into that user account. And specifically, we want to make sure that those failures do not have interspersed successes. So in this situation, we're looking for at least 10 login failures with no successes interspersed between them, followed by login success. So if you have 5 login failures, login success, 5 login failures, login success, we don't want to match. If you have 10 login failures and then a login success, we want to be able to match. And so you might think, based on the previous slides, that you would do it using some combination of the syntax from those 2 slides, and that is actually not the case. Here you actually end up using something called named windows. Previously, we used anonymous windows. So you create a window called login failure window. That's the name of the window. And our login failure window looks back, again, 5 minutes like before. The types of events stored in our login failure window are login events. And then we have 2 statements. So the login event type has a Boolean property, login success, that indicates whether our login event is a success or a failure. When we see a login event that's not a login success, we look at the event, at the ID of the event, and our events are guaranteed to have a unique identifier. We look at the ID of the event, and we look into the window at the IDs of the events stored within the window. If we are faced with a new event that has a distinct ID that does not match anything in our window, we add it to our window. So this is the when not matched, then insert select star. Finally, when we have a login event that is a login success, we use something called select and delete, which has very interesting semantics. So it looks very simple, select and delete from login failure window having count at least 10. And so what this does, if we have at least 10 failures in the window, they get selected out and emitted as a match, and also deleted from the window. If you have fewer than 10 login failures in the window at the time the login success comes in, we still delete all the events in our window, but we don't emit a match. So we start fresh. So say we have 5 login failures, see a login success, our state is cleared. So to put it all together, we have a single continuously running Flink job. And the stages in the Flink job are more or less as follows. So first of all, we ingest the events from the source. We then parse them and subject them to sanity filtering. So we have more or less a custom common format to all of our events. So earlier in the pipeline and way before Flink, we receive log lines from our customer infrastructure devices. They're then normalized into what is effectively more or less a JSON document with some standard fields. By the time that those events get to Flink, they have been normalized. We then parse them and subject them to sanity filtering. I will talk about the sanity filtering a little later, but one example where sanity filtering can come in is events from the future. So because we process everything in event time, we have to be very careful about not moving the clock forward too fast, because that'll create all sorts of queues that we don't really want to deal with. And when we can potentially see sometimes events with timestamp from the future, that typically indicates configuration issues. But we want to be able to catch that and not let that affect the runtime of the job as a whole. Once we've done that, we do the usual. We extract the timestamp from the event. We do watermark assignments. We use the out-of-bounded orderedness watermark extraction facility, and we apply actually different delays depending on the types of events for some things. And then we use the split stream operator to create a stream per rule. And split stream operator is deprecated in the newer versions of Flink, so we will have to find a way past that once we get there. For now, though, this actually is a very convenient way for us to create a different processing pipeline for every one of the patterns we want to match. Once we've split our big stream into a stream per rule, we very aggressively filter events of interest for every one of the rules. So as I mentioned before, we have 13 billion events coming in. Only a very small subset of them is actually of interest to any one of the patterns, any one of the rules we want to be able to apply to the streams. We want to call them as early as possible to basically save resource utilization, especially memory. And as well, we convert our events, which have many, many fields, and uncompressed, a lot of our events can range from 1,000 to 1,000 bytes. We select only the fields that are of interest to every particular rule and convert our events to tuples. Tuples are very easy for Flink to deal with. You know the events are very compact. Once we've done that, we apply keybuy. So we do a shuffle. Every rule comes with its own partition key that makes sure that unrelated events are processed in isolation. And so for example, going back to the successful brute force login attempt I was talking about before, the partition key for that one may be the customer ID and the username. So login events that share a customer ID and a username are processed together, where one of those values does not match. They're actually processed as effectively multiple different streams. Once we get past the keybuy, we actually get into the Esper operator, which is perhaps the more interesting part of this. The Esper operator is a glue code that we wrote ourselves that integrates Flink and Esper. The Esper operator is instantiated on a per rule basis, and it contains EPL, potentially multi-statement EPL, that defines the logic of the pattern we want to apply to the rule. We use the same approach as Flink CAP to reorder the events according to the timestamp. So typically in Flink, the absolute order of events doesn't really matter and doesn't come up that much. All you really care about, does it actually lie within your window or does it not lie within the window? However, when you want to express the notion of followed by, absolute order comes into play. And what Flink CAP does, and what we do as well, is we use a priority queue that is ordered by timestamp. When a watermark comes in, we dequeue all the events that come before the watermark, and we forward the events to the Esper engine, which the Esper operator instantiates. The Esper operator also registers a subscriber to listen for the output from the Esper engine. Finally, once we get results from Esper, we format them in our standard but custom AWN event format, and we emit them into the rest of our pipeline. And here I want to say that I'm describing right now one of the services we use for threat detection at AWN. There are others, and we actually built the service fairly late in the game, relatively speaking, relative to the life cycle of the company and some other services. And so this service right now exists more or less off to the side. So it gets events once they're done being parsed, once they're done being enriched. At that point, it processes them. There is a common escalation service which handles escalating events to our security analysts. And once we get output back from Esper, we submit these matches to the escalation service. The escalation service does another filtering pass where it could potentially apply whitelisting. So you can imagine a scenario where a rule is generally useful and generally has high value, but you want to be able to whitelist a certain IP address for a certain customer or a certain username, et cetera, because of whatever reasons. The escalation service takes care of that for you. And then whatever survives this final filtering pass is then escalated to review by a security analyst. So there's human eyes on everything before it goes out to the customers. The security analysts review our match. They review the security incident, apply their own judgment, and if they believe it to be worthwhile and warranted, they escalate the issue to the customer directly. So a little bit about more deployment. So we use AWS EMR, Elastic MapReduce. Pretty much everything our company uses is deployed in AWS. Why EMR? It was the easiest way to get going 2 years ago, to be honest with you. Flink supports more deployment scenarios now than it did before. Kubernetes is something that we are finding very, very interesting, but we have not really had the chance to fully investigate Kubernetes and Flink and how to make a transition. So for now, we use EMR. It's a managed Hadoop environment. So effectively, you ask AWS to provision a Hadoop cluster. You tell it how many nodes you want to have in the cluster, and you tell it you want to install Flink on it. EMR, you can ask for a bunch of different things to be installed. You can ask for Spark. You can ask for Ganglia. You can ask for any number of things EMR supports. We ask for Flink. We currently still run Flink 1.4.2, which is not the latest version by any stretch. The Flink version is determined by the version of EMR we ask for, and we're not on the latest version of EMR necessarily either. We've had some issues achieving stability when testing out upgrades, so for now, this is where we are. In our cluster, we use M5 2x large nodes, and this is meaningful to you if you're familiar with AWS, and if you're not, so it's 8 virtual cores, 32 gigs of RAM, and because of that, we assign 8 task slots to every task manager and 1 task manager per node. So today, we're at over 30 rules running in production. We process over 30 billion events a day within Flink. What gets forwarded to Esper is a much smaller subset of that. And we achieve that with 6 M5 2x large instances. So I want to go back to the diagram of our data sources that I started with a little while ago. So we have a very heterogeneous mix of data sources, and we want to be able to look for patterns within data sources, potentially across data sources. We've been able to achieve a lot with our current solution, with Flink, with Esper. There are some things that we have not really been able to express with Esper where we have to fall back more on batch processing using different technologies. And I want to talk a little bit about that, some areas where we would like to improve and grow in the future. Unsurprisingly, pretty much all the difficulties we have hit with, flow of time. So different data sources, different delays. Our sensor, when it observes an event, it sends the event more or less instantaneously. We have very few of any issues there. Similarly, on-premise infrastructure devices, so firewalls, et cetera, they send logs without any delay. They come in, not much of an issue there. Cloud data sources, a much bigger issue. And this comes from two separate considerations. First of all, our sensor pushes events to us. On-premise things like firewalls, et cetera, push events to the sensors, which then push events to us. Cloud data sources, we pull them. So first of all, there's a delay attributed to polling. And then you have a delay attributed to guarantees provided by the API. So for instance, Office 365, which is a very common suite of applications that we monitor for our customers, if you look at the fine print, you see that some things can appear hours, sometimes potentially over a day after it actually occurs. What do you do with that? You have to make a decision. How long do you wait? Do you wait so long that you basically introduce a latency to when you start emitting events, or do you go back afterwards and clean it up afterwards? We actually employ different latency allowance for cloud than for everything else, which means that when cloud data sources come into play, we can't correlate them using this system with, say, events observed by the sensor. If we need to do the correlation, we have to use batch processing and do it after the fact. Time zone adjustments. So we operate entirely in UTC. Our customers obviously do not. We normalize all timestamps that come in to UTC. That requires a fair amount of effort to make sure nothing slips by. Sometimes there may be data source that was misconfigured for whatever reason. And if that happens, you will potentially end up with the aforementioned timestamps from the future. So that's something you want to be really careful about, because that'll really mess with your watermarks. These are all things that we would like to investigate more in the future and potentially come up with better solutions for. So just a bit of a recap. We talked about the types of attack chains, the types of patterns we want to detect in our streams. We talked about what kind of data sources we ingest from our customers. We talked about what Flink offers us. We talked about what Esper offers us and how we put it all together. I've been very impressed personally with both the combination of Flink and Esper. They both have their own strengths, and I'm sure that if we were starting today from scratch, we might do some things differently. In 2017, this was by far the best solution we could come up with after doing the research, and it's held up very well over the past couple of years. Thank you very much. Any questions?
Thank you. How you integrate in the Esper state with the Flink checkpointing mechanism?
So we cheat a little bit, and we actually don't. We rely on replays to recover, to fill in gaps where we need to. Esper has a product called Esper HA, which is it's an add-on product where potentially you could integrate. It emits a stream of bytes where you could checkpoint the state. Today, we don't take advantage of that, and we handle gaps a different way.
So the kinds of computations that you're performing inside Esper look like they could be expressed in almost the same way or just slightly different syntax in Flink itself. So I guess that kind of raises the question, could Esper programs be compiled directly to Flink job graphs? Is there any work in that area, or is kind of having one system call out to the other really the best way to go about it?
It was definitely the best way for us to go about it when we started on this path. Flink has come a long way in the last couple of years. Mm-hmm. I'm not aware of any work of compiling EPL to Flink itself. There are some more complicated use cases that I haven't really gone into, where I think it would be a little tricky, but it's definitely an interesting area to explore.
So when you get really late timestamp data, like coming from the cloud, do you side channel, side output, put it somewhere? Do you drop it? Do you log it? What do you
So we don't drop anything. So the service I was talking about here is one of our detection services. We have more or less a pretty much distinct pipeline that handles the more common non-stateful case. And so we use two different data backends. One is Elasticsearch, and one is S3. So pretty much everything, all the events that come in, end up either in S3. They end up both in S3 and in Elasticsearch. We have different retention data frames around both of them. And so whatever queries we might need to run against late writing data, today we do it using batch.
Anyone else?
Couple of questions. One is that you deal with many different data sources. Do you have something that ingests the data and normalizes it? And do you have to keep rewriting it for every new data source that you have, or do you have a different way of doing it? I'll ask the second question also.
Sure.
This streaming solution actually seems to work on smaller time frames, whereas the APD kill chain thing can actually go back many timestamps before, like months ahead, right? How do you deal with that?
So I'll answer the first question. Jonathan will cover the second question. So yes, there is a normalization layer, which I have not discussed here, which happens entirely outside of Flink. We're actually primarily a Python shop. Flink is the only Java service that we use. We initially developed everything in Python. There is a normalization layer. We have parsers for the data sources we support. There are a lot of parsers, and yes, it is a constant effort to write new ones and maintain them. We have people more or less dedicated to that. So log lines that come in from customer devices undergo a normalization layer, where Flink operates on the normalized events. And then, so for the second question.
Yeah, and the best part of that is when the data source changes the format without telling you or telling anyone. It's kind of a headache. In terms of the time, it's definitely more of a challenge than the short time periods that we're looking at here. So we have within our security team, we have a number of internal business processes that are looking at the client data on a more holistic long-term time period. So they're hunting for those attack chains, looking for indicators of that. So we have indicators that would be for each stage of that attack. And piecing it together, we do it automatically through here, but we also do it manually through our team. And our team subdivides their clients, subdivided by their expertise area and things like that. And so that is more of a human business process driven work rather than the automated, more system generated work.
To just very quickly follow up on that. So I realize only now all the time frames I gave in the examples were basically 5 minutes. We do have some patterns that operate on time frames up to a day inside of Flink. So it's not just limited to 5 minutes. Some of them are longer, hours, up to a day. I don't believe we go much past a day at this point. Also, this system, this pipeline, it's a tool in toolbox. It's not the complete solution like Jonathan was saying. So we have both automated and human passes that try to capture things in different ways.
Thanks for the talk. You had mentioned 30-ish rules, and this is just a part of a larger solution. Are the 30 rules non-overlapping? And if you trigger multiple rules or other signals that you're trying to surface to the customer, how do you give them a sense of what's more important rather than less? Is it passing through a human layer that is doing some sort of scoring? And does that add delay to the time between the event occurrence and the signal generation?
Yeah, so what Ray mentioned previously about one of the other more singular non-stateful observation, that takes all the events in the queue, runs it through a set of rules, and does the prioritization and sorting and the determination and whitelisting. And there's a lot there. And also it runs, once a match is emitted through there as well, it runs through our human analysts who are looking at it, who are looking at the threat and looking at context. So they're provided with all the contextual information from all of our data sources for that client, for that device, or whatever value that they're pivoting off of in order to make a more contextual decision on whether to alert the client. And that does induce latency latency, obviously. The actual tool for the prioritization, not as much, but the human aspect for sure. So one of the things that we do is try and build as much contextual information into this system, which decreases the amount of time that they have to spend on investigating that event. But in general, it's a matter of giving our analysts the information that they need quicker and letting some of the lower priority indicators go into the 10 to 15 minute time frame rather than the quick that, say, a ransomware indicator would necessitate.
Cool, thanks.
Thank you.
Thank you all for being here. We're going to break for lunch now.